Okay, so question 2, I'm going to build on the same approach that I used for question 1. There is an alternative approach you can use for this, superposition, but we'll do the same approach. So we're basically going to be summing up our forces in the x direction. We're going to be taking positives going left to right. For our free body diagram, here we can identify that we've in effect got 4 sections to deal with. So we've got a change in geometry here, and then we've got a bolt drilled in, probably, with a force being applied at that bolt. So where that is, that defines a section here to here, and again we've got this bolt being applied, and that's going to define a section. So we've got 4 sections: section 1, section 2, section 3, and section 4. Okay. So when I cut through section 1, I'm going to be doing the same kind of idea, that I cut through my object and I will be exposing my internal force in section 1, where I throw away all the diagram to the left of me at that point. When I start moving through the bar, I will then be cutting through the bar and then exposing F2. Okay, and then I throw away everything left of me. And when I look right of me, the 2 internal forces that where I had my previous cut, they both counterbalance. So you can kind of do this using one free body diagram, where you just imagine that you're walking through the bar and that these internal cuts are progressively being exposed. Okay. So let's start off with what we would do as default. So we've got a reaction force RA here. I'm going to define that as going left to right, and a reaction force here, RE, define that as going left to right. Okay, so if things are negative, it's not a big deal. Just know that the reaction force is going from right to left if I get a negative answer. Okay, so let's do it. So we'll start off with resolving our forces, just the external ones. So I've got RA. I've then got this force here, so we're going to work in kilonewtons, so plus 60. Then I've got this force here, so plus 40. And then I've got my last reaction force, RE, equals 0. So RA plus RE equals minus 100 kilonewtons. Cool. So now let's go through my bar. We'll go from left to right. We'll take our first imaginary cut at the F1. We throw everything away of the diagram left of us of this cut, and we're exposed the internal force F1. Then we look right of us. Well, the only thing we can see right of us is RE equals 0. So you can say that F1 equals RE. What next? Let's do the cut F2. So ignore everything to the left of the cut. And what we've got right of the cut? Well, we've got an F2, which is going right to left. We've got a plus 40. And we've got plus RE equals 0. Let's rearrange this. So we've got F2 equals RE plus 40. Next one. This is a bit surprising because when I throw everything left of me and then I look right of me, I get a very similar result as before. Minus F3 plus 40 plus RE equals 0. So I have F3 equals RE plus 40. And then the final cut, notice I'm not going to go all the way to the end to the RA. So I'm going to throw this bit of the diagram away to the left and then look right of me. So I'm going to have minus F4, all the other internal forces balance, so I ignore them. And then now I've got plus 60, plus 40, plus RE. So now when we look right, we can now see this force here, you see, equals RE equals 0. So F4 equals RE, and now we've got plus 100. So we've got 1, 2 unknowns there, another 4 here, so we've got 6 unknowns, and we've got 1, 2, 3, 4, 5 equations. So we need a sixth equation, and the sixth equation we're going to use is how far does, let's say, the point E move? Well, we know we can work that out by looking at the internal forces of each section times by their length divided by their Young's modulus and their cross-sectional area. And we know that E isn't going to move. So we know that when we sum up all these things, we're going to get 0, which seems a bit pointless exercise, but the point to it is that we've now got a sixth equation where we can substitute in our internal forces F1, F2, F3, F4 into this equation here. Once we do that, we have RE times by length 1. So what's length 1? Length 1 is this distance here, so that's going to be now you could be a bit naughty here because you're going to end up with L, E and A values all the way through your equation, and it's equal to 0, so it's a homogeneous equation where it's equal to 0 basically. So that means that when we replace our F's, we don't have to worry about the units. We know that our final answer is going to be in kilonewtons. So I'm going to be a bit naughty and not worry about my units. So here the length of this section is 100 millimeters. Here we're brass and its Young's modulus is 105. The area, okay, so we're going to use a fluid mechanics trick here. So area equals pi d squared over 4. So the pi and the 4, it's almost a bit like units again. They're all going to cancel out. The only thing I need to worry about is the d squared. So what's the diameter of this section? Well, it's based upon 30 millimeters, so I'll put that in there. So those who've done fluid mechanics, you're probably quite used to the fact that you are going to cancel out pi's and 4's. So that's my first term from this equation. Now let's look at the next one. So we're doing the F2. F2 equals RE plus 40. We're still brass, so we've got Young's modulus 105, and its diameter is still going to be 30 squared. Now we move on to section 3, so force 3. In that case, we've got RE plus 40. I forgot my length there, sorry, which was 100. Let's do that a bit tidier. It doesn't look like it's to the power 100 there. Okay, so F3, we've got RE plus 40. What's its length? It's a length of 120 millimeters. We're now using a different material, and the material is steel, so it's got a Young's modulus of 200. Its area is going to be pi d squared divided by 4, but all the pi's and the 4's will factorize, they'll cancel, so ignore them. What's the diameter? It's 40, so you need to square it to make it into an area. Okay, let's do the last one. RE plus 100. So that's how equals 4. The length of section 4 is 180. Divide that by Young's modulus of steel, which is 200 gigapascals, and it has a diameter of 40. So that to be 0. So you can then work out all those terms, and you should find that your RE is equal to minus 37.2. You're working in kilonewtons, so this is kilonewtons. So then you can take this result and go back to here, put that in, and then you'll find your RA, and you'll find that you get a minus 62.8, and that's also going to be in kilonewtons. So look at your results here, and we see that that matches up with C. What did I say last time? Okay, so that's that one done. Try the algebra for yourself, and you should be getting these results. If you're not comfortable with the fact that I've used the trick of ignoring the units and ignoring the pi's and the 4's, try doing this equation using correct SI units, and you'll find that you're going to get the same result.